What's up guys, and welcome to this video on the 2018 supplementary exam. We're going to be going over question 3, kinematics, but before that I just want to go over two questions from this previous video that I just made. Okay, so I want to go over question 2.3. Okay, so it said calculate the height from which the ball was dropped. Okay, so we used the area under the graph to calculate this height, but you could have also used UVATs because it's undergoing constant acceleration. So for 2.3 we could have also used UVATs. Okay, and our initial velocity would have been this velocity 0. Our final velocity would have been 3.2. Our acceleration would have been the gradient, which we calculated as 6.4. T would have been 0.5, and we would be looking for S. So we could have used v squared equals u squared plus 2as. Okay, so that would be 3,2 squared equals 0 squared plus 2 times our acceleration of 6.4 times s, and solving for s gives us an answer of 0.8, which is also equal to our height, okay, and it's the same answer as before. So just another method. And also for question 2.6 also could have used UVATs. Okay, and you should get the right answer. Okay, cool. Now we can move on. Okay, so question 3, kinematics. Okay, two players kick a stationary ball at the same time. The defender kicks with a force of 180 newtons west. Okay, so that's also been shown, while the ball is also kicked forward at 160 newtons. Okay, assume the time between them is the same. Okay, so question 3.1. Calculate the resultant force acting on the ball while the ball is being kicked. Okay, so the first thing we should draw is our vector diagram. Okay, so we know, okay, so what do we know? We know the force of 180 is acting westwards. Okay, so we have 180, and we know that's 160 newtons. Okay, so this would be our resultant. Remember, we have the heads of the arrows must be touching for the resultant, and we have head to tail here, so that's a head, that's a tail, that's a head, and that's a head, that's a tail. Okay, but for the resultant we need to have a head and a head of the arrows touching, so we have this arrow right here. So this is the resultant. Okay, and we know that's a 90-degree angle, so by using Pythagoras we can say that r squared, let's do it in black. Okay, so we can say that r squared is equal to 180 squared plus 160 squared. So r is equal to 240,83 newtons. Okay, so a vector must have a direction, so our angle is going to be this angle here, theta, and we can say that tan of theta is going to be our opposite, which is 180, over our adjacent, which is 160, and therefore theta is going to be equal to 48,37 degrees. So r is going to be 240,83 newtons at an angle of 48,37 degrees. Let's say, okay, we know that this direction is north, so this is going to be west, so the angle is going this way, so it's going to be west of north. Okay, cool stuff. So that's the final answer. Let's put a box around it. So this would be your final answer, which would get you your full 4 marks. Okay, so the ball is at the position shown in the diagram. The ball leaves the players at a speed of 18 meters per second. the ball experiences frictional force from the grass and the air, the grass in the air, and accelerates at 2.5 meters per second. Okay, so calculate the distance traveled by the ball before it stops. Okay, so this 3.1.2, we're looking for the distance traveled before it stops. It experiences a constant acceleration, so we can use UVAT. Okay, so our initial velocity is going to be equal to 0. Sorry, our initial velocity is going to be the velocity at which it leaves, which is 18 meters per second. Our final velocity is when it stops, which is 0 meters per second. The acceleration is given as 2.5 meters per second squared. The time is unknown, and the displacement is what we're looking for. Okay, so now we can use the formula v squared equals u squared plus 2as. Okay, so we have 0 squared equals 18 squared plus 2 times the acceleration of okay, question 3.1.2. Okay, the ball is at a position shown in the diagram. Okay, so it's 6 meters there and 1.5 meters there. The ball leaves the player's feet, so this would be a velocity of 18 meters per second. The ball experiences a frictional force from the grass and the air and accelerates at 2.5 meters per second. Okay, so something to understand here is that this ball is slowing down. Okay, so this means that this acceleration is the magnitude of the acceleration, and the acceleration is actually equal to minus 2.5 meters per second squared, because it's slowing down, it's not speeding up. Okay, cool stuff. Knowing that, we can go into question 3.1.2. Okay, so calculate the distance traveled by the ball before it stops. Okay, so it experiences a constant acceleration, so we can use our UVAT. So UVA TS. Okay, so use our initial velocity, which we know is 18 meters per second. Okay, final velocity it wants as it stops, so it would be 0 meters per second. The acceleration, like I said, it's slowing down, so we must include the minus 2.5 meters per second squared. The time is unknown, and the distance is unknown as well, because that's what we're looking for. Okay, so we can say that v squared equals u squared plus 2as. Our v squared is 0 squared equals 18 squared plus 2 times minus 2.5 s, and solving for s, we get s is equal to 64.8 meters, which is our final answer, and we get 3 marks for that. Okay, then the next question asks, will a goal be scored? Okay, so to understand that, what we first need to do is understand it gives us the criteria. Okay, so in order for a goal to be scored, the ball must go into the goal mouth. Okay, so it must be within that goal mouth and must cross the goal line. Okay, so we've got two criteria, basically this 6 meters and this 1.5 meters, and both criteria need to be met. Okay, so 3.1.3. Okay, so we know the total distance traveled is equal to 64.8 meters, and we also know that this is acting at an angle of 48.37 degrees west of north. Okay, how do we know this? Because the displacement is going to be equal, the direction of the displacement is going to be equal to the direction of the force. Okay, so basically what we know is we have this angle here, theta. So this is basically, if we were to draw a kind of diagram of it, it would look something like this. So okay, so it's 64.8 meters, this angle 48.37. Okay, so we need to figure out that distance here, let's name that A, and this distance here, B. Okay, so in order to score a goal, okay, let me just give myself some distance. Okay, so in order to score a goal, A must be less than 1.5 meters, and B must be, remember, if it's less than 1.5 meters, that's that distance right there. So anything inside that would result in a goal, and B must be greater than 6 meters. Okay, so we know that that's also a 90-degree angle, so we can use basic trig. Okay, so let's say that B, well, let's start with A. A is equal to 64,8, yeah, 64,8 sine of 48,37. Okay, so A is going to be equal to 48,43 meters, and we know that that's north, so it's going to be west. Okay, so A is greater than 1.5 meters. Okay, so what we can basically say, it misses the goal here. Okay, so we know he's actually not scoring a goal, but let's just do B anyways. So B is equal to 64,8. This time it's going to be cos of 48,37, and the answer for B comes out as 43,05 meters. Okay, so B is greater than 6 meters, so that would result in A, that's far enough. Okay, but because of this criteria right here, because he misses the goal, we can say that, will a goal be scored? No, no goal is going to be scored. Okay, and we've got the calculations to prove it. Okay, cool stuff. Let's go on to this question, 3.2. Okay, a hot air balloon is rising vertically upwards at a constant velocity. Okay, so basically we can say, yeah, constant velocity. The cell phone is accidentally dropped from the balloon when the balloon is at a height of 404,4 meters, as shown in the diagram. The cell phone strikes the ground 6 seconds after it is dropped. Ignore air resistance. Okay, so calculate the velocity or the speed VB with which the balloon is rising when the cell phone is dropped. Okay, so constant velocity. Okay, so we know that this is also a constant acceleration problem. Okay, it's a free fall problem right here. Okay, so free fall problems, we always use UVATs. UVATS. Okay, so we know that then we're trying to calculate VB. Okay, so U would be our VB. Okay, when it strikes the ground. Okay, so the scenario we're going to use is between when the cell phone leaves and hits the ground. So when it hits the ground, the velocity is going to be 0. Okay, the acceleration we're going to be taking upwards, take direction upwards as positive. Okay, so the acceleration would be minus 9.8 meters per second squared. Okay, and we don't know the time. We do actually know the time. The time is 6 seconds. And we also know the displacement is minus 104,4 meters. That's seconds. Okay, so to calculate VB, we're going to use the equation. Let's use S is equal to UT plus a half AT squared. Okay, so S is minus 104,4 is equal to U, which is VB, times T, which is 6, plus a half times minus 9,8 times T, which is 6 squared. Okay, and so there's only one unknown here. There's only one variable, VB. So we can solve for VB, and VB is equal to 12 meters per second. Okay, so 12 meters per second, it asks for a speed, but we also know that that would be, yeah, so we don't need to give a direction. Cool stuff. That's 12, that's 3.2.1. Okay, 3.2.2. Okay, so we've also get 4 marks there. State the velocity or state, yeah, the velocity at the instant it is dropped. Okay, so at the instant it's dropped, remember this hot air balloon is moving upwards, so when it's dropped it's moving upward, it reaches its height and then hits the floor. So the velocity would be the speed, so the velocity is 12 meters per second, and with the direction, and remember it's moving upwards when it's dropped, so it is up. There we go. Okay, question 3.2.3. Okay, calculate the maximum height that the cell phone reaches above the ground. Okay, so we can use UVATS once again. UVATS. Okay, this time we're going to focus on the condition. The criteria is going to be between this distance right here. So it's between when it leaves the hand or gets dropped to when it reaches its maximum height. Okay, so U we know is 12 meters per second, and we're taking up as positive once again. Okay, 12 meters per second. V, when it reaches a maximum velocity, it's going to be 0. The acceleration minus 9,8. T is unknown, and S is also unknown because that's what we're trying to calculate. But we should have enough. We can use the equation V squared equals U squared plus 2AS. Okay, V is 0 squared is equal to 12 squared plus 2 times minus 9,8 S. So S is equal to 7,35 meters. Okay, so we know that distance right there is 7,35. Okay, but it says calculate the maximum height that the cell phone reaches above the ground. So the maximum height is going to be the height that it's at already, which is 104,4, plus the height after it's been let go, which is 7,35 meters. Okay, and so the maximum height is going to be equal to 111,75 meters. Okay. Okay, question 3.2.4. Okay, so calculate the height of the balloon when the cell phone strikes the ground. Okay, so what we do know about this hot air balloon is that it is traveling at a constant velocity. Okay, this tells us a lot because what we do know then is that the velocity is equal to the displacement over the time. Okay, we also know that VB is the velocity of the balloon, which is constant, which is 12, is equal to S over, and the time taken for it to hit the ground is 6. So S is equal to 72 meters. Okay, so the total distance between the balloon, so S between the balloon and the floor, which is when it hits the ground, is going to be equal to 104 plus, or 104,4, 104,4 plus 72, which is equal to 176,4 meters. Okay, and that's the answer to that question. Yeah. Okay, cool stuff then. Thanks for watching, guys. That is the end of the question, and in the next video we will do question 4. So thanks for watching. I hope you found it useful.